Welcome to this video that will go over the solutions to the Monte Carlo integration activity within the Part B lecture notebook for Module 4. So as usual, you should feel free to create as many new code and markdown cells as you would like to as you go through this activity, just to pull code and examples from other places, do experimentation, whatever. I just always like to mention that. Now, in this example, if you try to run all in the notebook when you first get it, you'll see that you get a syntax error here. And that's by design. I haven't completed this part. If you notice, I have two things. You're supposed to complete this part of the code and this part. I've done most of the coding for you, and I've left the empty parts for you to do. Let's read the instructions and say, what's supposed to go in here? So you're creating a wrapper function. That's a new theme that we seem to see a lot now. It's dating back to the homework in Module 3 and what we've seen in Part A and in Part B. Of Module 4, we have these wrapper functions. So we complete a wrapper function, multiple 1D MCApprox in the code cell below, except that now we assume n is a list of integers, just like what we did above with the rectangle rules activity. It's going to contain the different number of random points used to approximate the integral. Because this is a Monte Carlo approximation, it's based on sample averages of randomly generated numbers, as opposed to rectangles that are deterministically computed. The wrapper function also has an additional parameter, number of trials, which is an int type that specifies the number of times, meaning the number of trials, to repeat the approximations for each value in the list of n values. The default of numTrials is set to 10, as you see here. The function should output a two-dimensional array of shape length n, right? However many n's there are, we have here, and the number of trials, which means that the ij component in our Python syntax, which in Python indexing starts at 0, should give the j plus 1th Monte Carlo approximation of the integral using the ith number of random points in the array n, right? Or in that indexing matches up with that. So you need to then finish this. What you need to do is say, okay, I need to create this zeros array. So here I'm creating an array. It's not like an empty list that I was appending to before. Now it's an array. I'm having you do different things in different places. I already tell you what it needs to be. You just need to say, I need this to be length n, and I need it to have number of trials, which is an int type. And again, you should add a doc string when you're all done with this. You should add a doc test. You should add code comments. I highly recommend that. I'm not requiring you do that, and I'm not going to do it in the video for the sake of simplicity, but it's good to go through. Now, for each n value, which is how many random points we want to generate a random approximation of the integral, and we want to repeat that several times so we can, in the end, analyze results the way we were doing above with, like, histograms and the variance decreasing or standard deviation decreasing. So let's just go ahead and come down to this. Say, okay, we need to compute, for the ij, we want to compute a Monte Carlo approximation of the function f with this number of points in. So let's go ahead and look at what the compute 1D Monte Carlo approximation looks like. I'm going to pause the video for just a second. All right, I am back. Sorry about that. I just had to pause. My wife just got home with groceries and I was checking to see if I needed to help bring them in. Okay, let's go back to compute 1D the MCApprox. So you pass it f, a, b, and n, enter the number of random points. Just as a refresher, you compute the random uniform points between a and b, and then you compute the sample average of the function values evaluated at f evaluated at these random x values, and then you multiply it by the length, the measure of the set that you're integrating over, which in this case is the length of the interval, so it's b minus a, and then you do that Monte Carlo approximation. You take that length of the interval, and you multiply by that average value, and then we see, we want really just the second value right here, right? When we look at these integral approximations, we've done this before, we say we want return the second value. Remember Python indexing at 0, so we return 1. So when you come here and you say, I have to change this right here, I have to do this, I say, okay, I want f, I want a, I want b, and I want n of I. I said this here, n of I. N is an array now. I need to pass it for I in the range length. And if you look, I'm doing this a little differently because I want to give you different flavors of how you can do the iteration. For I in range of length n of I I need to pass it n of I here. And then I want to return the second component of that function, which has the integral approximation. So that's it. If you do that, this code now runs. We remove the syntax errors, and you've completed the first part of this activity. And as usual, for a number of different lambda functions, including f of x equals x, f of x equals x squared, and at least one of your choosing, you could use the same ones you used for the rectangle approximation activity that was the first activity in this notebook. I ask you to again compute the errors for the Monte Carlo approximations of the integrals with, in now I give you this array, and I go from 10 to 100 to 1,000 to 10,000. You could literally, I wrote this in code format, so you could just copy and paste that here. That's going to be used for all of them. And now you just need to call this function. Well, let's go ahead and do this. Let's make, our lambda function f of x equals x. And let's look at our Monte Carlo errors 1. All right, we're going to kind of follow a theme that like what we did before. And this is already returning an array. It's not returning a list like the first activity. I'm doing things in slightly different ways just so that you can, see when you need to cast as an array, when you don't. This is already an array. We just need to subtract off the integral value. So we're going to just call this function multiple 1D MC approx. And we're going to pass it the f. We're going to pass it a equals 0, b equals 1, and n equals n. And then we are going to I'm just going to use the number of trials default, which is 10. We can, of course, in fact, I'll just go ahead and change it. I think it's sometimes nice. It gives you a little bit more accurate results if you do a few more trials. It just takes longer. If you go beyond 100, it's going to take maybe a couple seconds to run if you do like 1,000, because it's looping through all of these so much. This is returning the array that I want. I need to subtract off the exact value. Now, of course, you can come up to your previous activity with the rectangle rules and look at how we were doing this here when we were computing errors, right? We were just subtracting off the quad. This is for that same function, f of x equals x. So I'm just going to come back down here. There we go. Subtract off that quad. That's going to give me, this is a scalar. This is a float value that will be returned. It will be subtracted from every component of this array, because that's what happens when we subtract a constant from an array. So that's it. It's a little simpler than before. And I don't think then I need to repeat. You could do f equals lambda x squared, or you could just put, again, the lambda functions directly in here. It's up to you. Just make sure to call that errors 2, errors 3. I like to create the function f here because it's called both here and here. And that means when I copy and paste this code and then change this to a 2, all I need to change is that to like x squared, and then I can copy and paste this again, change that to a 3, and change the f to either x cubed or whatever the other function is that you'd like to use, or in however many times you do this. Just very simple changes at that point. But I'm just going to do that, so I'm just going to make sure I ran that again. But you need to do it for all the other different lambda functions. And then for each of these different lambda functions, create 2 separate log plots with a legend that shows the means and the variances over the number of trials. I'm not saying standard deviation here. I am saying variances of the computed errors versus the number of random points used in the Monte Carlo approximations. For the means plots, you should compute the absolute value of the mean errors, because the mean value of the error could end up being a little bit negative. So you need to take the mean of, the absolute value of the mean. Do not take the mean of the absolute value. Do not do that. You'll see what I'm doing. And then, okay, well, I'm just going to go ahead and start plotting this. So I want to show plots that are kind of like this to visualize the rate of convergence. I'm just going to go ahead and copy and paste that down below. For here, create 2 separate log plots. So you could do this as subplots. So you could say like like 1 equals plot dot, add subplot, or we could do like, let's see, was it plot dot subplot? There we go, subplot. And we can make 1, 2, 1. And then I think we would change this to ax1. And we're having n, remember n, I'm calling this n here, not n's like I was doing before. And I said, do the log plot, do the absolute value of our errors MC errors 1 mean. All right. And axis 1, I believe that is correct, although we'll see. And so there's my axis 1, and then I want my, on that first set of axes, this would be the absolute value of MC error versus number of samples for f of x equals x. There we go. And this will be, again, x. This is x1. That's the title for that. Now, let's just go ahead and run to see if I did this right. There we go. We see it there. And I'm also going to do this. Let's see, did I do it? Yes. So I took the absolute value of the mean. Yes, that is correct. And I can just copy and paste this down. I want to have the second plot. I don't see a, oh, you have to, when you're using axes, you have to do set x label and set title. There's just a slightly different thing than if you're using that PLT command when you're doing that. Let's just see to make sure I did that right. Yes. And maybe in this case, it's better to do it so that they look a little better. Do 2, 1, 1. So we're going to do 2 rows, one across, so that they have a little bit better shape. So the title, there we go. That looks a little bit better. And then here, when we do the 1, 2, 2, so yeah, 2. See, let me go ahead and, you're hearing me kind of fumble over it a little bit in the moment. Here, let me go ahead and copy and paste that now because I've changed the subplotting. Now the plot we're going to put below it is the variance. I said I think to do the variance of MC error versus this. We don't need the absolute value anymore because variance is a positive value. We'll take the positive value and take that variance. All right. I think that all looks good now. I was just checking something above. And there we go. Ooh, and we need a little bit of space between these figures. Well, you can resize it. It's in this mode where you can resize it. So I have this widget mode. Oh yeah, those things are kind of just grouped together. I need to give some space, maybe change the different sizes of things. So I could also do it here where I create subplots as well. So I could do like fig equals plot dot, let's say figure. I'm going to do, actually I'm just going to make it a bigger figure too. Oops. What I need to do is do size equals 8, 8. And of course I messed that up. Why am I doing it like that? I'm going to pause for just a second because I'm just kind of blanking on doing this right. Okay, I'm back. I'm just having a kind of the brain fog for a second. The best thing to do is just make it like a plot dot subplots, make it a big plot there. I think that should fix things. Yes, that looks better. There we go. So I just made a big plot there. Again, plot dot subplots. I don't know why I was forgetting that. With the fig size equals 10, 10. You could change this to whatever you want. I mean, you could go back to like 8, 8. That's what I was doing before. Yeah, that seems to do. I think 10, 10 was better with the fig size. So in this case, 10, 10. You can play around with it however you want, but I think you get the basic idea. And so here, the interesting thing is we're seeing this error looks like it's converging down, the absolute value of the Monte Carlo error. So they're between 10, -2, 10, -4, like what's going on? Like these are supposed to be unbiased estimates. So it's just the fact that we have like this number of trials is 100. That's actually kind of a small number. Watch what happens when I go up to 1,000. I just want to demonstrate this real quick with the f of x equals x. Because if I run that doesn't take too long to run. Let's look at this again. All right, this is the absolute value of the mean error. Now look at it. It's like 10 to the -4. It's like it's all jumping. There's no, you'd say like, it doesn't look like there's any convergence. The overall values of this though, since it's going like 10 to the -4 for all of them, they're going to go to 0. It's just the mean error is unbiased error. So you're just kind of seeing whatever you're getting from a sample mean, from a random average. And it's not going to be exactly 0. It's going to be near 0. And how variable it is from 0 is a function, or that it can be, is a function of this trial size. Like if I go up to 10,000 trials, so now this is going to start taking a little longer. See, it took a couple seconds. And I plot this again. I bet you this goes down to like 10 to the negative 5 at this point. That's my guess. Okay, 10 to the negative 4 still. I mean, I bet if I run it again, it's going to be a different value each time. But this is always going to be like the same. So, okay, did it run? Yeah, it ran. Let's run this again. See, now this looks like it's just kind of some random variations because the mean value is an unbiased estimator. And it's going to be about 0 for the mean error. We're taking the absolute value just so we can plot it. But this is kind of a meaningless plot. I'm having you do it just so you can see you can plot it. But just because you can plot something and it might look like it has a type of convergence, I'm doing this because, in a sense, a lot of times you can be tricked by having code run, give results that seem somewhat intuitive, like convergence plot you see, but you could arrive at easily the wrong conceptual, theoretical conclusion because you're not thinking about what it is you're actually plotting. And plotting the mean error here doesn't actually have any meaning. Like I'm just having you do it. And then in the end, I ask you to try to, comment on your results in a markdown cell. What I'm trying to see is like, did you see weird results in the means? And could you explain why they were there? What was going on? And why these results were not really changing, no matter what things you experimented with these number of trials. So that's it. I just kind of wanted you to experiment with that and see that impact a little bit. You want to go really nuts here. This is going to start eating up memory. You're going to see this memory going up. And eventually, if you start seeing that you're eating up too much memory, you should go over to here on the notebook where the stop button is. And you should shut down some open notebooks or restart your kernel to free up memory. But I'm just going to go ahead and do one more, which is kind of nuts. So in fact, getting to this point, maybe I want to do like 1e to the 5. So I think I was just doing 10,000. So this is 100,000 trials. So this is now taking, look at how long this is taking. We'll also look at the memory because we're creating big arrays. So this is going to take, we'll see this memory usage go up here, I think. And in a second, boy, this is taking, right? It takes a few seconds. Very interesting video time. I'm going to pause the video until it's done and then come back. As soon as I paused the video, it was done. Okay, so it didn't take up too much more memory, actually. I thought it would take up at least a couple more megabytes. But let's run this. Okay, yeah, well, I'm just going to rerun that because of that 20 figure warning. But yeah, again, this looks like it's converging down. But if you look at the overall value here, this is down at like 10 to the negative 4 for 10 to the 1. But it's down to like 10 to the negative 6 here. So these values keep going down on this vertical axis for the absolute value of the mean error as we shrink. If we were just plotting the actual mean values, they're all reasonably close to 0. Whereas these values do not change. This is always the same. And so I am, by the way, not suggesting that you do something as insane as like 100,000. I shouldn't say insane. As kind of ridiculous as 100,000 trials for these examples. I think 1,000's good. 1,000's a pretty reasonable approximation of everything. But you just have to be wary of like interpreting this as saying, oh, the mean's converging. No. It's just for low sample numbers, you're naturally getting more variation in each estimate. So it takes a lot more trials for this average error to go down. But you see, if I use less trials, then I can get more like the sample mean can just be a little bit more variable, but it's all the average of the averages. If you use the number of trials to be large enough, this goes down, right? We just saw where it was down to like 10 to the negative 4, and now it's up towards 10 to the negative 2. It's just because of the wide variation of estimates when you're only using 10 samples to approximate an integral. But again, this value is not that different. Even though we're using bad estimates here, the variance in those estimates is reasonably approximated. And again, I know probably feels like I'm belaboring the point. I'm about to stop. Just do this for different lambda functions. You're going to see very similar things because it's kind of independent of the function and the dimension and everything. That's the nice thing about Monte Carlo. And just comment on these results. Try to summarize some of these take-home messages. But I'm going to stop here, have one more short video to make that's on this part of the lecture notebook about what happens if you need to integrate over a set that's complicated. Thanks for listening.